All right, hello. Oh, you know what? Let me check my distance on the board. Yeah. What's up? What it do? How you doing? Think I got a little bit more space on the board this time. Hello, everybody. Thanks for joining me today. How are you doing? How's your Tuesday? Yeah. I know last time I talked about going over fractions, and I didn't quite make it to fractions. I did vocabulary because vocabulary is essential. It's crucial in understanding math. And so, of course, I wanted to start with that. And then, as I said, I've changed my video recording device. So now I am limited to 30-minute videos, which from what I hear is a little bit easier to watch anyway. So I'll try to stay more focused and get through more information. So where did I leave off? So I do want to step into some of the fraction operations today, but I know there's a few words that when we talk about vocabulary, there's some fraction vocabulary I want you to recognize. So the top of the fraction is called a numerator, which I think most of you know, but N-U-M-E-R-A-T-O-R. The bottom of it is called denominator. And one of the things I did, because you know I'm a dork and I'm goofy and I love my math, so I remembered that the denominator goes down, like, you know, it goes down in the DM, but right now it goes down in the denominator in a fraction. Goes down, denominator, so that's the bottom number. Remember, your denominator represents how many pieces it takes to make the whole part, okay? So that's what that is. And then this bar in between, this right here, this line, is called a fraction bar. And so just knowing that, like I said, fraction bars are actually part of grouping symbols when you are trying to follow your order of operations. Because you know that P represents parentheses, but that also stands for all grouping symbols. So parentheses, brackets, fraction bars, absolute value bars, square roots, all of those are grouping symbols. So yeah, and you need to know that a fraction bar is a grouping symbol. The fraction bar represents the mathematical operation of division. Okay, so, and then a few more things that you want to know is that fractions are also called rational numbers. Rational numbers. And this is important when you get further down in your college algebra and stuff and you're doing your work, because you'll have rational functions. And you'll have to remember that no matter what, in all cases, fractions cannot have the denominator of 0. What else? We have proper fractions and improper fractions. Proper fractions and improper fractions only differ in what the numerator looks like, so to speak. So proper, and just think of a proper setting, you know, you're properly seated, you're using proper vocabulary and stuff. And so it's natural for the number on top to be smaller than the number on the bottom, right? That's going to be a proper fraction. And it's proper again because your numerator is smaller than your denominator. That means I need 5 parts and I only have 3 of the 5. When we say improper fraction, that means our numerator is larger than our denominator. We might have 17 over 9. That's an improper fraction. That means we have 17 parts. We have 17 pieces, but we only need 9 to make one full piece, you know? And so when you're dealing with improper fractions, that's also where you get your mixed numbers from. And your mixed numbers, your improper fractions lead to mixed numbers. And they're called mixed numbers because they're mixed because they have one whole number and a fraction added to it. And so again, If fractions always represent division, no matter what, at the very end, you're always going to divide. And it's always going to be the numerator divided by the denominator. So in this sense, we have 3 divided by 5. That means I want to see how many times can 5 fit into 3. And you're like, 5 can't fit into 3. Well, it can. This is where your decimals come into play. You know, and over here, you're going to have what I call, again, like we said, is a mixed number. When I'm thinking about how many times can I fit 9 into 17? Well, we know 9 times 2 is 18. So if you're going to actually do this division, you would have 17. Watch how I do this, you guys. Well, I always said, you know I'm a dork, right? So thump it. Boom. I hate fractions. I love fractions, but y'all hate fractions. I hate you, I hate you. So you come to the left and you thump it. Ah! And you thump it and it's going to fall over. Oh my God, I fell. And then the 17 is going to land here. The fraction bar is going to be here. The 9's right here, and it fell this way. Yay! I have all kinds of little stuff. So how many times can we fit 9 into 17 without going past it? We know that that is 1 time. You multiply these two, for those of you that forgot how to do long division. Then we subtract this value. And we know we have to borrow from this, do all of this. The remainder is 8. So your mixed number is going to be your whole number, 1. 9 fits into 17 1 whole time, with 8 out of that 9 left over. So that's how you get your mixed numbers. And just because I'm not officially teaching and this is my personal video for you to use, I'll go ahead and talk about this is how we go from improper fraction to a mixed number. We actually do that division. To go from a mixed number to improper fraction, I call that a popcorn method. So say I had the improper fraction or the mixed number of 4 and 7 out of 9. So I like to call this the popcorn method because it looks like a piece of popcorn. You're going to multiply your denominator times the whole number, add the numerator, and it goes over the denominator. See, looks like a piece of popcorn. So we're going to do 9 times 4. I'm going to actually make this a little multiplication dot, and then I'll make this a plus 7, right? So 9 times 4 is 36. 9 times 4 equals 36, and 36 plus 7. 6 and 7 is what, 13? Makes 43. So my final answer would be 43 over 9. So this is from mixed number to improper fraction. And this, where'd my orange marker go? That's not mine. I think this one is. This is to go from improper fraction to mixed number. Okay? They say you shouldn't teach opposites, but you know what? Whatever. I teach in color, that helps, right? So, again, we have our numerator, denominator, fraction bar. Fractions are also called rational numbers. You can make a ratio. You know when you're saying, oh, 3 out of 5 guys say this, or 10 out of 15 people say that. When you write 10 out of 15, technically, like you could write it like 10 out of 15. But you typically, normally, without even thinking about it, you write 10 out of 15. And that's normal. That's what it is. That's what makes it a rational number. Okay? fractions, improper fractions, fraction bars. All right, and so every single integer is a rational number. So we know, go back, integers are signed numbers, right? They're any numbers from 1 to 1 million indefinitely, and from 0 to negative 1 million indefinitely. So from negative infinity to positive infinity, we know that those are numbers. They're called signed numbers. The official name is an integer. And so what I'm telling you again is that every single whole number, every single number, period, can always be a fraction. And this is something that you're definitely going to need as you advance in your math courses. You have to remember that every single whole number can be represented as a rational number. Meaning, you see 4, we know that it's 4 over 1. Right? And I think I might have talked about this a little bit before. Every 100% of rational numbers can be expressed like this. Whole numbers, they can all be over 1. Yep, you can even put this over 1 if you wanted to. Yes, you could. Okay? So, again, you're going to need to know this. You're going to have to remember that every single whole number is always a fraction. And now I do vaguely remember talking about this because I told you, you see a value. But what's really going on with the value that you see is it's 4 over 1 is 4 to the first power, 4.0, 1 times 4. Remember? Yeah. So again, that's where all that comes from. That's the rule. Okay, every single whole number or every single number can be written as a rational number. All right. Something else you probably want to keep in your mind, keep practice, keep good on, is equivalent fractions. Fractions that have the same value, right? What that looks like is that you have 1/2, you have 5/10, we have 30 over 60. All of these represent the same value, and that value is half. Those fractions are called equivalent fractions, fractions of equal value, and they won't always reduce down to 1/2. That's what we did. We reduced it down. Here, I found a common factor. Remember when we talked about factors and multiples and stuff? So I know 5 is a factor of 5 and 5 is a factor of 10. 5 goes into 5 1 time. 5 goes into 10 2 times. Over here, I can use 10 or I can use 3s. If I use 3s, 3 goes into 30 10 times. 3 goes into 60 20 times. And then I would just simply use, oh, okay, well now I can use 10. 10 goes into 10 1 time, 10 goes into 20 2 times. So see, they all are the same value. They're all 1/2. But so that makes them equivalent fractions, even though they look different. And that's what you're going to do a lot of too, a lot of reducing. So you're going to have to be really good on your factors, okay, and your multiples. If you have something like, where's the spot for me? Let's say you have 8 12s, right? And you're like, okay, is this reducible? Hopefully you see, well, they both have a factor of 2, so I know I can divide 2. And if that's what you have to start with, or maybe you want to start with the prime factorization. However you want to do it, whatever is more comfortable for you, whatever you remember, that's what you want to do. I know 4 goes into 8 3 times, and 4 goes into 8, sorry, my bad. 2 times, 4 goes into 8 3 times. So 8/12 and 2/3 are equivalent fractions. They are fractions that have the same value. And so you want to think about this as like making change. You know, if you give somebody $1 and they give you 4 quarters back, or if you give them $1 and they give you 10 dimes, or be it $1 and 100 pennies, they're all the same value. But in each situation, they have a different use. So kind of think about that. You know, that's called reducing, it's called simplifying, it's called putting it in its lowest terms. All of those are the same. Reducing, simplifying, lowest terms. Okay, these are equivalent. They have the same value. One more term I want you to be familiar with, and that's called reciprocal. Reciprocal means to flip, right? So the reciprocal, if I say that means to flip, let's take this. The reciprocal of 8 over 12. Well, if we flip it, that's going to be 12 over 8, right? So here's the key thing that you need to remember about all integers being rational numbers, okay? Because if I ask for the reciprocal of 4, you write me 4. I'm going to say, what's the reciprocal of 4? 1 over 4, right? Reciprocal. 1 over 4. So yes, it means that you're flipping it. You are now making your denominator the numerator and your numerator the denominator, right? So reciprocal of 17 over 9 is, you better have said 9 over 17. I say right. Reciprocal of 43 over 9, 9 over 43, right? Okay. I hope you guys don't like start this in the middle. You're like, what the hell is all over her board? Yes, that's how it goes in class. So you can say, wait, let's talk about the orange. Wait, let's talk about the pink. Let's talk about the purple. Nonetheless. All right, so I'm going to erase all of this now because you can pause it and go back. That part's so cool. All right, I'm going to erase all of this and talk to you about what's next in the book. I want to play fractions with you. You're like, play fractions, what is that? Well, because I get pieces of paper and rip it up, and it's just nothing like making that fraction come to life in front of your eyes. You know what I'm saying? So everybody's like, I don't know about fractions. But you do know about fractions. If you use the words like, ooh, in a minute, almost, halfway, partly, or anything like that, you're using a fraction. You know what I'm saying? So this is what I used to tell people. Remember that piece of paper we tore up? I'm going to grab another one. Hey, you like my hair? Yeah. All right, so talking about fractions, just to help give you a visual of what a fraction is, where it comes from. One piece of paper, right? This one. How many pieces of paper do we have? One. And to have this one whole piece of paper, how much do we need? One. Yay. So we're going to tear it in half. Tear it in half, fold it in half. So what I want you to recognize is that as you, right now, we have one, right? One piece of paper, and it's in one piece. Now, so we have one piece of paper, it's in one whole piece. We only need one to make that whole piece. 1 over 1 is the equivalent of the number 1, okay? But now we've torn our paper in half. So, how many pieces do we need to make one whole piece of paper? Now we need 2 pieces, right? And how many do we have? Well, we have 2 out of that 2. And again, that makes one whole piece. But now since we need 2 pieces to make one whole piece of paper, that's what we need. Notice what we need is the denominator. It goes on the bottom. What we need is the 2. But if I lose one, I only have 1 out of the 2, which, as we all know, is half of that piece of paper. Take your pieces, tear them in half again. Hopefully you have some paper. Grab some paper, do this with me, so you can kind of see it. So if I tear both pieces in half, then how many pieces will I need to make one whole piece of paper? If I tear both pieces in half, how many pieces will I need? I hear you. Say a little bit louder. Yes, you are correct. I will need 4 now because I've torn those in half. That one piece of paper that I started with, right? Well, now it's in 4 pieces, and I have to have all 4 pieces. I have to have all 4 pieces to make one whole piece, right? Okay. What if I tear all 4 of these in half? If I tear all 4 of these in half, now how many do I have? I have 8. So notice what's happening. The more you tear your paper, the more pieces that you have, right? The more pieces that you need to make one whole piece. Because if I lose 2 of these or 3 of these, I'm definitely not going to have one whole piece. Then I only have 5 out of the 8 that I need to make that one whole piece. So again, what I want you to be attentive to is that as you increase your pieces of paper, your denominator gets larger, because that's how many pieces you have. If we tear all of these in half, then we'll need 16, all 16 pieces to make one whole piece. And if we tore those 16 in half, we would need 32. So you see what's happening again. As we tear all of this in half, our denominator gets bigger, but we know the actual pieces that we need are getting smaller, right? So put that in your head. Don't let that go anywhere. Keep that locked in. The bigger your denominator, that just means your pieces are broken up into that small or that many amount of pieces. But then you have to say how many parts you have to the whole. How many parts do I have to mix the whole piece? And so what I really, like I said, I want you to recognize that it grows as your denominator gets bigger, right? That just means you need more pieces to make one whole piece. All right, what is, let's say out of the 16 we had 7, and out of the 32 we had 9, and out of the 64 we had 19. What's the reciprocal? 8 over 5, 16 over 7, 32 out of 9, and 64 out of 19. And everything you should, or something you should always do every single time at the very end, you're like, is this reducible? Does 9 and 32 have a common factor? Do 19 and 64 have a common factor? Even if that common factor is as small as 2. Then start with that. Check 3, check 4. And so you might want to find something, go look up, Google your divisibility rules. That will help you find some common factors. Okay, what else do we have? All right. So there's like fractions. Like fractions are fractions with the same denominator, not that big of a deal. Told you to look up your divisibility rule. Yes. Let's see. To build a fraction, to make a fraction bigger, you're going to, now this is the part that's usually confusing for people. Because say I have to add some fractions, right? And so you know we have to go back to the rule of adding fractions. To add or subtract fractions, add and subtract rational numbers. They must have, can y'all see that? Same denominator. So this is for adding and subtracting, right? So that means that whatever you're adding and subtracting, if it does not have the same denominator, they cannot be added. Also, then don't forget that denominator values are typically the same, are not added. We'll say that because they're not added. So what that means, let me give you an example, is we'll say that we're trying to add or subtract. We're going to say 1 over 7 plus 4 over 7. So because both my denominators are 7, I can add my numerators. But that just means, now think back to what we did with the pieces of paper. One is torn into 7 pieces, and this one is also torn into 7 pieces. So they're torn into the same amount of pieces. So I can say that 1 plus 4 leaves me with 5 out of 7, right? Because 1 plus 4 is 5 sevenths. But if I had, I don't know, 4 over 7 minus 2 over 7, then that's going to leave me 4 minus 2, going to be 2 over 7, right? So those are going to be called like fractions because they have the same denominator. So what do you call fractions that do not have the same denominator? I'm waiting. Unlike fractions. Yes, they're unlike fractions. So that means, let's just say you had 4 over 7 plus 3 over 9. Now, think about cooking, right? Because when you're cooking something, or maybe you do fashion, or something like that, maybe you're in your medical field, you know that these measurements can't be, like, you can't add tablespoons and milliliters, right? You have to figure out how many, like, what's that amount, right? You have to make it both the same. Probably a bad analogy, but I'm talking to a camera, not a real crowd, so it's a little challenging. But essentially what we have to do here is we cannot add unlike fractions. They have to have the same denominator. So what can we do? That is where your multiples are going to come in play. Because you're going to find the least common multiple, right? That's when you remember that word, LCM. And least does not mean lowest. It means the one that's not as common. So typically it's going to be the biggest number that they both share. So usually I'll say list your multiples: 7, 14, 21, 28, 35, 42. Wait, is that right? 1, 2, 3, 4, 5, 6. Yep. 49. And then, wait. Oh my God. 8 times 56, there it is. 9 times 7 is 63, and then 70. Then I'll go by nines. 9, 18, 27, 36, 45, 54, 63, 72, 90, right? So I always say, hey, list your multiples. That's going to help you find the least common, the one that's not as common multiple. Now, I think I might have time to show you something to make a little bit more sense. But for now, you list your multiples, and then you determine what number do you see that they both have. So running through here, I'm looking, oh, they both have 63. Right? So when I look at my multiples of 7, 63 is the 9th multiple. So remember what I told you about having all the pieces? 9 over 9 is 1. So basically we're just multiplying this fraction by 1 to change the way it looks. That whole 4 quarters from $1. And you remember whatever we do to one side, well, we're not in the equation, so I'll retract that part. But we got the 9th multiple of 7. We have the 7th multiple of 9. And we're multiplying. So I always thought it was weird that when you teach fractions and they teach you to add and subtract fractions, like they already presume that you can remember multiplying fractions. And I forgot about that part because I forgot I was supposed to teach you to multiply fractions because that's the easiest thing. It's numerator times numerator, denominator times denominator. So that doesn't